Now that we've started talking about currents, we need a way to establish them in a circuit. The easiest way to do this is with a battery, and we can consider the battery to be a source of EMF or electromotive force. This is not a great name. It's not a force, it's a potential difference. Why would we want to start calling a voltage some kind of force? Well, we're going to see there are some problems with the idea of voltage. We'll see that soon. And there's at least going to be a not stupid reason for talking about voltage in terms of force. That's all I can tell you right now. It'll probably be less painful later when we learn more about it. Now, the idea of the battery is there are chemicals in it that react in such a way as to create a potential difference between the two terminals to push charges from one side to the other. There are a bunch of important physical properties about a battery. The most obvious one is its voltage, or what a voltmeter would read when we connect it across the terminals. Turns out if we connect the terminals of a new 9-volt battery to a voltmeter, it'll really read about 10 volts, and your car battery, which you probably think of as 12 volts, is closer to about 13.8 when it is fully charged. Now, if you've ever been stranded by a car that won't start, and this happens more often in the winter than the summer, and needed to get somebody to jump your car to jump start it, you might have thought about carrying a spare battery. The problem is a spare car battery would be very heavy and expensive and take up a lot of room, and you'd need some way to maintain the charge on them so it couldn't just sit in the trunk. You might think if the car battery is around 14 volts, maybe we could connect two 9-volt batteries in series, meaning the plus terminal of one goes into the minus terminal of the other, and then we connect our device we want to power to the free plus and minus terminals. These would fit in the glove compartment. They only cost a couple of dollars. They last for years. This would be a great way to jumpstart a car. You may have already figured out this won't work. One of the other important physical properties a battery has is its maximum current, and this is connected to something called its internal resistance. We can model a real battery, like they do in your book, as an ideal battery, like we've been using, plus some little internal resistance R that there's no way to separate. We act like there's a little resistor in there, but of course there's not. What's really causing this resistance is the chemical reaction can only happen so fast. That limits the current the battery can put out, and it therefore acts like there's a resistor in the path that we can't get away from. One of the reasons the car battery is so big and heavy is that it's filled with a lot of thin lead plates. If we have more plates, we have more surface area for the chemical reaction to happen, which means it can deliver more current, and it has effectively a lower internal resistance. A car battery may have an internal resistance of about 20 milliohms or so. The 9-volt battery probably has an internal resistance closer to 10 ohms, so the current you can get out of it is going to max out around an amp, where the current coming out of a car battery could be several hundred amps. Now, we write the voltage we measure at the terminals of the battery as the EMF minus IR, where I is the current we're drawing from the battery and R is the internal resistance. As the battery ages, R increases. This means we can't just check with a voltmeter to see if the battery's healthy or not, and the reason is the voltmeter draws almost no current from the battery. It puts virtually no load on it. So the terminal voltage reading is very close to this E, our expected voltage when it's new. As soon as you put it in a circuit that has a significant draw, you'll have a larger value of I, and that R that has gone up since you bought it will reduce the terminal voltage to something too low to be useful to you. This is why real battery testers actually test under a load. They're not just voltmeters. Now, as we saw with capacitors, resistors are available in a variety of values and tolerances, but not an infinite variety. So we sometimes need to combine the ones we have to make different values. This means we use them in series or parallel. This figure below will help us see what does that little internal resistance mean. For right now, we'll keep pretending that this battery V1 is a perfect battery, but this process is going to help us understand how to handle that internal resistance. So let's say we take our perfect battery and connect 3 resistors in series. We can ask, just as we did for the capacitors, what single resistor could take the place of these 3 and put the same load on the battery. We now know the formula for making a cylindrical resistor the resistance is resistivity times length over area, we could imagine that all three are made of the same stuff and they have the same cross-sectional area. In that case, the resistance difference would be the same as the length difference. Like we did with the capacitors, let's imagine we bring them closer and closer together until they're ultimately indistinguishable from a single long resistor. That resistor's resistance would be rho over A times the total length, or rho L1 over A plus rho L2 over A plus rho L3 over A, and that's just R1 plus R2 plus R3. So we find that for resistors in series, the equivalent resistance is the sum of the individual resistances. This is the opposite of what we got for capacitors. We got this for capacitors in parallel, but this is the way it works for resistors in series. This means the equivalent resistance is always larger than the largest individual resistance. We also can see that the current through each resistor has to be the same, since when charges go from R1 to R2, they have nowhere else to go but through R3. There's only a single path here through this circuit, so the current has to be the same everywhere, because otherwise charge would pile up, that would build up a voltage that would stop the current. That's how you make a capacitor. Now, what about if we put resistors in parallel? We have this set up here. Here we notice each resistor has the same potential difference across it. That's the key thing about things being in parallel. The total current from the battery will be the sum of the currents through each resistor. Using what everybody calls Ohm's law, we know that I equals V over R, so we could say I1 is V over R1, I2 is V over R2, I3 is V over R3. We add them all together. That's the equivalent of V through the equivalent resistance. That's going to be V over R1 plus V over R2 plus V over R3. We divide by that common voltage, and we see that 1 over the equivalent resistance is the sum of the reciprocals of the individual resistances. This is what we got for capacitors in series, but here we're talking about resistors in parallel. This means the equivalent resistance is smaller than the smallest individual resistance. Now, as a side note, a lot of times you hear electricity takes the path of least resistance, and that's not correct. Electricity takes every path, but in inverse proportion to the path's resistance. Now we could do what we did with capacitors, where we took a sort of a complicated mess, this system of many resistors, and we see how could we find the voltage across and current through each one of these. This looks like a pretty big mess, but we're going to do just what we did with capacitors and simplify it, redrawing it each time. So, the top two resistors, these are in series. They can simply be replaced by what we'll call RA, which is their sum, 300 ohms. The four on the right are in parallel. 300, 400, 500, 600. We take the reciprocals, we get 0.0095. This is not the equivalent resistance because we forgot to do the 1 over R. I left the units out so that wouldn't tip you off, but if we keep the units in like we should, we would have inverse ohms here, and you'd realize, oh, I still have to flip this over. So when we do that, we get that RB, the equivalent of these four, is really 105.3 ohms. If you want, you could call the 700 ohm resistor by itself RC, or you can just call it R7. The last two we put are in parallel, so we call them RD, and we have 1 over RD is 1 over 800 plus 1 over 900, or 423.5 ohms. Now we have four resistors in series, so our equivalent is just their sum. We add them all up and get 1528.8. So if we had a single resistor of this value, it would look exactly the same to the battery as this mess of resistors looks. Now, the current through that single resistor would be battery voltage over resistance. We get 0.0157 amps. If that's the current leaving the battery, we can go back up here and see all that current has to go through the 100 and all that current has to go through the 200. Now we know the current through those two. If we know the current through them, since V equals IR, we know the voltage across them. It's 1.57 volts across the 100 ohm resistor and 3.14 volts across the 200 ohm resistor. Now, when the current gets to the four resistors in parallel, it will split up. We know the current through our imaginary RB would be this 0.0157 amps. So the voltage across it would be that current times its resistance, or 1.653 volts. So if there's 1.653 volts across each of these four resistors, I can figure out the current through each of these four resistors, again using V equals IR. We solve this and we get progressively smaller currents through each one as the resistances increase. We get 0.00551 amps, 0.00413 amps, 0.00331 amps, and finally through the 600 ohm, 0.00276 amps. If we add all four of those currents up, what do you think we get? Well, we get the 0.0157 amps we said we had in the first place. The 700 ohm resistor has to carry the full battery current also, since it's by itself. So the voltage across it, 10.99 volts. Finally, our last resistor, the imaginary RD, also carries the same current, so the voltage across it is going to be 6.65 volts. That means we get currents through these two resistors of 0.00831 amps and 0.00739 amps. If we add them up again, we get 0.0157 amps. Now, if we add the voltage dropped across each of R1, R2, RB, and R7, what do we get? 24 volts. And RD, I forgot. To within the rounding error. Now, when the resistors are in parallel, just like when capacitors are in parallel, we can't add the voltage across each one since the same voltage is across all of them. For a height analogy of this, if we have four separate 10-foot ladders going from the first floor to the second floor, that doesn't mean that floor is 40 feet tall. We could find the power dissipated by each resistor if we use P equals IV, but since these resistors obey Ohm's law, we could also write this as P equals I squared R, or P equals V squared over R. Again, the full 24 volts is not the V for any of these resistors, just as the full current, 0.0157 amps, is not the current through resistors that are in parallel and are sharing it. How will we measure these things in the lab? Well, very useful tool for this is the multimeter. We have these very cheap ones. They're less than $10. They can measure voltage and current and resistance. There's a little battery tester spot on here where you can put the battery under load and get an idea whether it's good or not. Some of these measure capacitance, inductance if you get more expensive ones. They can tell you about transistors and diodes, which we aren't really going to cover. Anyway, this is what they look like in general. You notice we got two probes, but three places they could go. Unless we're measuring high currents, we're just going to leave these two probes in the bottom two holes. The black one usually goes in common, and the red goes in the other one. There's not really any reason to not switch them except convention. Typically, we make black ground and red positive. Once we have this thing set up, we have to measure voltage between 2 points that we want to touch with the probes. Usually, we do this by putting the black probe, which is our common, remember, at the most negative point in the circuit, which is usually the negative battery terminal, and it's like our C level, and we consider it ground, although sometimes you can have a ground supply with multiple powers, a circuit with multiple power supplies, and you might have both negative and positive voltages referenced to that ground in the middle. We measure voltages across things like batteries and resistors, which means the voltmeter is set up in parallel to what we're measuring. The diagram below, we're trying to find the voltage across R2. This is a standard symbol for a voltmeter. It's just a little V inside a circle, and the two leads are on opposite sides of it. If we analyze this circuit before the voltmeter is attached, we know the equivalent resistance is R1 plus R2, so the current has to be V1 divided by that. Once I know that current, I can multiply that current by R2 to get the voltage across it. That would give me V1 R2 over R1 plus R2. This is called a voltage divider, by the way, and it turns out it's a really important circuit. For example, let's say you'd like to monitor your car's battery voltage and have something let you know if it drops below a certain level so that you don't need to get a jump start. You can buy a microcontroller for under $20 that could do the job, but the only problem is they can't generally handle voltages above 5 volts. If your car's battery is healthy, its voltage is going to be around 14 volts, and that would kill the microcontroller. Quick fix here would be to duplicate this circuit where your car's battery is here and it's 14 volts. This is your microcontroller input. And what two resistors could we put there that would fix this? Well, if this resistor is 9,000 ohms and this one is 5,000 ohms, then the voltage across this for a 14 volt battery, we can do the math and see we get 5 volts. So the microcontroller is fine. If the battery voltage drops to half of what it was, the voltage across R2 also drops to half of what it was, or 2.5 volts. We could use any two resistors with values in this ratio. So you might think we could use 9 mega ohms and 5 mega ohms, and we could if we could buy them. What about the power delivered to the resistors, though? What about if we use 9 ohm and 5 ohm resistors, very small ones, instead of 9,000 and 5,000? We get the same current, or no, I'm sorry, not the same current. We get the same voltage across each one, but the current is now 14 volts divided by 14 ohms, which is 1 amp. The power dissipated in the resistors would be 9 watts and 5 watts. This is not going to kill the car battery very quickly, but it will start a fire unless you have high power resistors, because that's an awful lot of power to dissipate in a regular resistor. On the other hand, if we use our 9,000 ohm and 5,000 ohm, our current is 1 milliamp, and the powers would be 9 milliwatts and 5 milliwatts, which probably wouldn't keep them warm. A big deal here is we don't want our measuring device to alter what we're trying to measure. For example, you've seen the foot-long glass thermometers in chem lab. We could measure the water temperature in a pool and we wouldn't really change the pool's temperature. What if instead we took that thermometer from this really cold building and tried to measure the temperature of a spoonful of coffee? We're going to cool it down a lot, and whatever value we finally get from the thermometer won't tell us much about how hot the coffee really was in the beginning. So having that in mind, do we want the voltmeter to be a high or low resistance device? Let's assume it's low, and let's put its resistance at 10 ohms and put it in the original circuit with 5,000 ohm and 9,000 ohm resistors. Let's redo the circuit, find the equivalent resistance. R2 and the voltmeter are in parallel, so we find their equivalent, and it's 9.98 ohms. Remember, it has to be smaller than the smallest resistance. That's in series with R1, so our total R is now approximately 9,010 ohms. What's the voltage across the R2 R voltmeter pair? It's 14 volts times a little less than 10 ohms over about 9,000 ohms. 0.0155 volts. This is nowhere near the 5 volts that we had before. The voltmeter has completely screwed up this circuit and it would be useless. On the other hand, what if we assume the voltmeter is a high resistance device and set its resistance at 1 million ohms? We go through the same process. Now we notice we haven't changed that equivalent resistance much from what R2 was. It's down to 49.75. Total resistance is 13.975. We run it through the same formula and we get 4.98 volts. That's very close to the real answer of 5. And most voltmeters actually have even larger resistances and they disturb the system even less. What about ammeters? In this case, what we're trying to do, we have to measure the flow of electrons through the circuit. So what we typically do is we break the circuit, we snip the wires, not really, but that's effectively what we do, and reconnect the circuit through the ammeter. Here, it makes no difference at all where we connect the ammeter because series circuit, we have the same current everywhere. Is the ammeter a high or low resistance device? Notice that it's connected in series instead of in parallel, so the total resistance in the circuit is R1 plus R2 plus R of the ammeter. Hopefully it's pretty clear to see here that in the series case, we want this to be as close to zero as possible so that we minimally disturb the circuit. Now, what's the downside of hooking things up wrong? Well, if we wired up the voltmeter like this, what would happen is we'd have our total resistance going from 14 kiloohms to more than a mega ohm. We would essentially stop the current and kill the circuit. If, for example, one of these was a light bulb, it would go out. That's not a big deal, right? You can realize what you've done and fix it. On the other hand, what if we connect the ammeter across a resistor instead of in series with it? So if we connect the ammeter like this, Now we've got two separate current paths there, remember. So what do we get out of that? Now, if we assume the ammeter is a 5 ohm resistance and we've connected it across a 5,000 ohm resistance, that combined resistance will look very much like 5 ohms. The current in the circuit is going to go way up, and almost all of that current will take the ammeter branch instead of the R2 branch. Now, in contrast to the voltmeter case, this can actually damage the ammeter. You can't send larger currents than it was expecting through it. In general, there's a fuse that will blow when you do this, but the thing is, if we have a $5 multimeter and we blow the fuse, we've essentially totaled that part of it. The downside for us is, instead of just not working, the meters we have will typically read nonsense after this happens, and people won't understand why. Last thing that we commonly do, we measure resistance, which we don't do in a powered circuit. We separate it out. And one thing that people commonly do is pinch the resistor leads onto the multimeter leads with the fingers of each hand. What you're really doing here is, again, creating a parallel circuit where the resistor is one branch and your body is the other. Typical value of resistance for your body with dry hands is around 1 mega ohm. If you try and measure a 1 kilo ohm resistor this way, this will be okay. You'll get 1 over 1,000 plus 1 over 1,000,000. 1 over that is 999 ohms, very close to the right answer. Now try doing it with a 2 million ohm resistor. You get 1 over 2 million plus 1 over 1 million. That's 667,000. That's very far away from your 2 million. So you have to keep that in mind when you're using this thing. When can you actually use that little shortcut of just pinching the resistor to the meter, and when do you have to stop and connect it in a more professional way?